Everybody.
Good evening, ma'am.
Good evening.
Happy National Science Day, Observance Day, calling on our chair-elect for 2024, Dr. Usha Rani, to kindly give an opening address.
Good evening. Am I audible?
Yes, madam. Yes, you are audible.
Good evening to all. This National Science Day is celebrated to honor the discovery of Raman effect and acknowledge the discoveries and innovations by scientists and promote the importance of science in our daily lives. National Science Day is celebrated on February 28th every year to honor the Indian physicist C.V. Raman for the discovery of Raman effect, for which he won the Nobel Prize also. So here we have a small event organized by IEEE WIE Bangalore Section Affinity Group and Council on Electronic Design and Automation, Bangalore Section Chapter. I hereby take the privilege of welcoming Dr. Srinivas, the Chair, IEEE Bangalore Section, Ashwini Holla, Chair, WIE Bangalore Section, and the speakers, Dr. UC Niranjan, Dr. Vimala P, and also the once again the speaker Ashwini for this small and wonderful event. Thank you.
Thank you, madam. I now call upon our chief guest for the event, Dr. Srinivas P, to kindly address us.
Hello. Good evening. I hope I am audible. Hello.
Yes, sir.
Someone
Sir,
can-
you are audible.
Yeah. Good evening. I'm very happy to be a part of this program to reflect a couple of my thoughts on the science. So it's a very important development in humanity, the scientific thought. From the beginning days of our primitive knowledge to the present, we have come a long way. And at this moment, we can say that we have quite learned a lot. The humanity has learned quite a lot about our nature, our universe, ourselves, and so on and so forth. So behind this is the human thinking in an approach called the scientific approach. There are many other slightly somewhat out of science approaches also, but gradually they have been getting into the scientific approach. Then from our learning or the knowledge point of view, if you see, then we have so many dimensions or so many subjects that we learn. Of course, the science has been divided into mathematics, physics, and so on and so forth. And of course, more recently, we have the technology. Even though you say more recent, it has been the technological progress of humanity has been there for quite some time. So I would like to trace, or I would like to recollect the development of humanity from the primitive person to the present day. If you look at it, there's a lot of development in our thought process, and also a lot of results, a lot of outcomes about ourselves, about our nature, and so on and so forth. In fact, I would like to include all aspects of the knowledge, not only science, the various branches of knowledge, which sometimes some of them may not be truly science, into this. Because see, the highest level of education that the present day system gives us is called the PhD. Starting from the school education to PhD and beyond, you call it philosophy. In fact, just before we call this science, all the knowledge was under philosophy. That's why you get a PhD. So I would urge everyone to reflect upon our thought processes, our beliefs, and various activities that we do in our daily life and associate a scientific approach to many of these things. One of the cornerstones behind this is the questioning attitude. We need to question, what is this? Why is this? And so on. That is at the corner of all the scientific thought, including the technology. In fact, if you observe, there's a lot of decline in support for science in terms of education, not exactly in terms of the real thought, but in terms of education. Not many people are taking up BSc and such science degrees. But of course, we have science and engineering. In fact, engineering or technology is also not so much different from, in fact, it is blended together. It's only a branch of knowledge, you can say. I hope today, everyone will think about the scientific approach and our thoughts and ourselves and rejuvenate our thought process and benefit. I would also like to compliment the Women in Engineering chapter or affinity group to organize this National Science Day program. In fact, women have been playing an important role in all our humanities since the beginning, even though at different points in history, we have different roles that women have been assigned. But right now, I would foresee that there is a lot more role for women in science. In particular, they can play a big role in the R&D that our humanity can take up. So with that few words, I would like to thank all of you for listening to me for a few minutes. Of course, my thoughts have been random, but I hope you will recollect in your mind and formulate your own approach towards our world and ourselves and humanity as a whole. Thank you very much. I hope that much is enough. Hello. Were you able to hear me earlier, whatever I spoke?
Thank you, sir.
Yes, I am
I
able to
now
hear.
call upon, hello, I now call upon our student representative, Ms. Salma Nadaf, to kindly introduce our speaker.
Now, and all present here, I am Salmanada from BIT Mangalore. Now, I'm going to read out the bio of today's speakers, Niranjan U and P. Vimla. Niranjan used to obtain his PhD in Electrical Science from Indian Institute of Science, Bangalore in 1993. He was a researcher at the Monitoring Institute, Fukuoka, Japan in 1904 and 1996. He is an professor. Yes, ma'am. Yes, ma'am. Hello.
Yeah, please proceed. Proceed.
Sir at ENC Department of MIT, Manipal, and former Director of Research and Training at Manipal.net Manipal. He is the President of BMESI and past Chair of IEEE Mangalore subsection. He was the recipient of IEEE EMBS Best Student Paper of 1992 at Paris Achiever Paper Award and ISDE, Arizona in 1996. He was facilitated with the Distinguished Alumnus Award by NITK during their Diamond Jubilee celebration in the year of 2019. UC Sir is the President, Biomedical Engineering Society of India, and Professor at the Department of BME MI. I welcome you, sir. Now I'm going to read out the bio of P. Vimla ma'am. P. Vimla ma'am received her BE and ME degree both in Electronics and Communication Engineering from Anna University. She completed her PhD in semiconductor design and simulation under Anna University, Chennai 2014. She is currently working as a professor department of ECT, Dayananda Sagar College of Engineering, Bangalore. And she has one publication, 50 in journals and 35 TEDx conferences and patent. One book published as editor and 10 book chapters authored. She had 300 projects from various government for funding agencies like DO and DXT. She has received IEI Younger Engineer Award in 2017, Women in Engineering Award in 2018, and Outstanding Scientist Award in 2020. Her research interest focused on modeling of a nanoscale semiconductor and device modeling and simulation using the both Centauris and Atlas T simulation tool. Currently, she is working with the analog and digital circuit simulation using GN, RFET, and CNFET. Thank you.
I hope the screen is visible. Is my screen visible?
No, not yet.
Yes, Ashwini ma'am, I can see this screen.
Sharing the slides.
Achievements
see me,
by
Ranjan?
women. That is the slide I can see.
Okay. Kindly give us a minute, please.
Ashwini ma'am, I can see achievements by women. That is the slide I can see.
Thank you so much. Sir, I will take your cue and advance. Take your cue.
Yes, I can see the
I will advance
slides now.
slides as and how you tell me. Thank you so much.
Okay. Sure. Okay, I'll start. Good evening, ladies and gentlemen.
Good evening.
I'm very... Pardon? I'm extremely happy to be present in this National Science Day event being organized by the Council for Electronic Design Automation and Women in Engineering Group of IEEE Bangalore section. I'm Niranjan UC. I'm the past chair of IEEE Mangalore subsection. I'm also the president of Biomedical Engineering Society of India. So Madam Ashwini told me to talk about achievements of men and women of science in India. So this is the topic she has given. As Professor T. Srinivas, our chair, mentioned today, science has made a lot of progress, especially in the past, 5-6 centuries. Ever since Copernicus formulated the theory of astrophysics that all the planets revolve around the sun, there has been tremendous progress, and it has been aided by the technological prowess and progress that the scientific discoveries have become huge. And because of the scientific discoveries, our life has become very, very comfortable, luxurious. When we compare to our forefathers, life has not been that very easy and luxurious. And thanks to the implementation of all the scientific theories and into putting into practice by making use of technology, this has happened. So in this brief talk, I mainly work in the Manipal Institute of Technology, Manipal, and I'm also working in the area of medical engineering, and our university is well known for medical school. So most of our progress, most of our work has been towards the area of medical technology. So I will share some of the views of mainly medical engineering as we teach in our institute. So the agenda is mainly medical technology, as I said, and also what is it that somebody has to be or somebody is considered to be very successful in the area of science, discoveries, and technological advancements. What is the culture? What is that is required? We will see during this presentation, and also uh, try to inculcate these values in oneself so that he becomes a successful scientist or a technologist. As Professor T. Srinivas said, one of the prime area or important thing in scientific discovery is questioning, and that is something which the students have to inculcate in themselves all the time, and we have to constantly engage ourselves in the continuous inquiry, and thereby achieve success in whatever which we do, and deeply engage ourselves in the tasks which are put in front of us. So when we look at the scientific progress, especially in this part of the world, that is South Asia and also mainly India, so what comes to one's mind is, before Christ, 500 BCE, it was the medical science of Ayurveda, which was very profound and which was put forth by none other than scientists whom we call as scientists as Charaka, and he has written a treatise called Charaka Samhita. No doubt they were all in the ancient language of Sanskrit in terms of shlokas, but now uh, these days, especially our former Vice Chancellor of Manipal University, Padma Vibhushan M.S. Valiyathan, has translated this Charaka Samhita and Shushruta Samhita into from Sanskrit to English. And I hope the slides are visible. This is one of the sculptures of Shushruta, which has been displayed in the Royal College of Physicians in Australia. And some of the instruments which were used way back in 500 BC for doing various kinds of surgeries uh, is all displayed here, and one gets really surprised and awed to see such modern science which was there during those times, and one really pats his own back, and it is a really a proud moment for India for having propagated the science of Ayurveda, the medical science. And thanks to the present views of the central government, we have a department of Ayush, uh, which propagates these knowledges of Ayurveda, Unani, Siddha, homeopathy science, which are alternative to the allopathy science. And we have seen that, whenever the allopathy, the English, the so-called English medicine fails, it is the traditional knowledge of the herbs and the roots and the uh, lifestyles which were propagated by the earlier science of Ayurveda, which comes to one's help. And today being, I'll go to slide number 4. Today being an event which is organized by the WIE, that is Women in Engineering Group, I take this opportunity to show slide number 4 of Lady Scientists, is a book in Kannada which is written by one of the
Sir, can
engineers
you
who.
pause a minute? Just a minute, sir. Can you just describe what you're seeing on your screen?
I'm seeing
Ashwini
nothing.
ma'am, I can't see anything actually.
Madhu, can you kindly share the screen that was shared with you today? Slide deck. Yes, just a minute, sir. Okay, I'm sharing my screen. So kindly don't share anything until I ask you to, please. Yeah, is this what you wanted to share?
Yes, but I don't see anything now.
Okay, so slide number 4. Madhu, are you able to share? Or Prasunna, madam?
Yes, madam. I can able to share, madam. I kept in
Yeah,
slide
thank you.
4 only. It's a sheet.
Yes, ma'am. Do start sharing.
Yes,
I've taken off my screen.
Yeah, I'm in slide number 4. Sir,
Yeah, I
is
can
there?
see this
Yes.
now.
Yes, sir.
Yeah.
Thank you.
So this is basically a woman engineer. I'm sure Professor T. Srinivas would know when I was studying, doing my PhD in Indian Institute of Science, we used to see the couple engineers and scientists, Dr. Chatterjee and Dr. Rajeshwari Chatterjee. And this is one of the pictures of the lady scientist, Dr. Rajeshwari Chatterjee, when she was a student in Indian Institute of Science. And we would see them always in the library. And she is the one who worked on waveguides and microwaves. And even after her retirement, they were very active in the campus of Indian Institute of Science, and we could see all of them in the library. And this is the book which is written by the former general manager of Hindustan Aeronauticals Limited, that is Dr. Miss Nemi Chandra, who has written about the lady scientists of previous generations. And being a lady, one has to fight against the patriarchal society, and very many times it is the husbands. And today there are more than 250 VLSI mixed signal design engineers in that place. And they are not only trained, and they do a cutting edge, state of the art, IC design work for multinational companies, mainly to Texas Instruments and many other multinational companies, sitting in a place called Manipal. Earlier, Manipal was known for, the university, but today it is not only known for the university and education, but it's banking, but it's also known for, such entrepreneurial journeys of new companies such as Manipal.net and Karmic and Robosoft and so on. Next slide, please. So I would like to take this opportunity to, when we started our Texas Instruments projects in India, the first Texas Instrument devices and then equipments were all arrived from, no doubt, from air, but they were transported to their place, their building in Bengaluru on Wind Tunnel Road through the very popular road, vehicle which is extensively used even today in India, which is the bullock cart. So as you can see in this picture, Texas Instruments moved all its uh, products and all its equipments on bullock cart to their place of work in Bangalore. And then today they have become one of the biggest offshore centers of Texas Instruments from Dallas, which does state-of-the-art, high-end technology work. Next slide, please. And apart from that, ISRO, one knows the space program of space science program of India, which is very, very good. And we recently had Chandrayaan also. And if you look at the first launching of the rockets from Sriharikota, from the space program of India, you will see that the test rockets were all taken on another modality of transportation in India, which is the bicycle. And you can see that bicycle carrying the rockets, and today we have reached, where uh, many of the developed nations are trying to get in there, but we had a very successful Chandrayaan program, and many such space programs are thanks to and also one of the presidents of India was Dr. APJ Abdul Kalam, who worked in the DRDO and was known as the Missile Man of India. Next slide, please. So India is known as the back end office of the whole world, especially in the IT. After 1991, we have made tremendous progress in the field of information technology, and we started from the very uh, measly beginning. And this is a picture of Infosys founders which I took when they were young. You can see Nandan Nilekani and Narayan Murthy and so on. So they started this, uh, you know, taking up the projects of IT and delivering it to the big companies. And they had a vision, they had forethought that IT would be a very big industry and big business, and it would be a big revenue earning component for India. And Bengaluru has become the Silicon Valley of India, and they have successfully started the Infosys company and foundation, and today they are one of the giants competing with the IT companies all over the world. Next slide, please. And this is a favorite picture of mine, especially when I talk to the engineering students. And this is a lady working on her IT project. And Ukraine is also, these days, many competitors from Europe and also from Asia and also from Africa are there in the IT space for companies in India. And this is a favorite picture of mine, a lady IT engineer in Ukraine keeps doing her job even when outside of her office, outside of her building, it is being bombed by another neighboring country. But she is focused on her delivery. She is focused on her time length, and she is focused on delivery of substantial work to her client. Next slide, please. So I would just like to end with this quote from one of the Nobel laureates who won Nobel award twice during his career. And he says it's not that he's so smart. He's being very polite. It is not that he's so smart, but it is just that he stays with the problem longer and then tries to solve the problem. So one of the essential things of a technologist or a scientist is to remain engage himself deeply with the problem which is at hand. Next slide, please. So I would like to end with some of the takeaways of this talk today is one has to develop an attitude and engage oneself very, very deeply and put all his efforts to learn the problem at hand. And one has to go away out of his comfort zone of, uh, good fat salary and, comfortable life and comfortable family, etc. One has to step out of his comfort zone in order to really contribute something significant to the field of science and technology. And he has to always look at the problem, and he has to try to solve those problems. And that is what engineers are looked upon for. And one has to have a great amount of perseverance. Even when he fails, he should never give up, and then he should try a new way, a new path. And today, with the advent of so much of progress in the information technology and all the technology which we see around us, opportunities are aplenty, and one needn't look at as job seekers, but they should look at their careers as job providers. And I'm very happy that many of our students have been able to do this. And with this, I'll end my talk with my last slide. And thank you very much for this opportunity to speak on this National Science Day at this event. Thank you.
Thank you very much, sir. We are touched beyond our words. Madhu, can you share your Canvas slide deck, please? Rasuna, madam, if you can stop sharing, Madhu can share his slide deck. Thank you so much, sir. I now call upon our next speaker, Dr. P. Vimala. Madam, are you able to share your slide deck?
Yeah, yes, ma'am, I'm able to do.
Yes, ma'am. Thank you. So while the slides are rolling, I would like to, Salma has already read out her bio well in advance, but still I would like to take some time and thank the chair of Council of Electronic Design and Automation, Bangalore chapter, Mr. Alokya Das, for suggesting that you speak in this regard. So over to you, madam.
Yeah, I hope my screen is visible in other end.
Yes, ma'am. It is visible.
Yeah, thank you, ma'am. Thank you. Maybe good evening, one and all. So today I'm going to give overview in the topic of technology advancement in the semiconductor space. So since it was a semiconductor, it's going to be completely the technical perspective. We know all like semiconductors are all very important in our every part of life. They are like a foundation of all modern computing devices such as smartphones, laptops, and all the medical diagnostic equipments. And also it can be used in routers, switches, and communication infrastructures. That is going to be the backbone of the internet, and it's enabling the global connectivity also. But when it comes to the sustainability, the semiconductor also plays an vital role. And today I'm going to give the overview for current semiconductor technology and what is going to be the future technology, maybe in the industry perspective, and maybe high level I will try to cover further research also.
Yes, ma'am. Next slide.
Yeah, I hope it's able to view my screen.
VLSI different levels.
Yeah,
Yes,
yeah,
ma'am.
yeah, yes, ma'am. So here, just I want to give an overview how this semiconductor is plays a role or it's having impact towards the electronic devices. We know like we are all using different electronic devices in our day-to-day life. All these electronic items are having billion of transistor inside it. The fundamental element or the basic element for this transistor is going to be the semiconductors. That is nothing but the silicon semiconductors. So here we have the overview for this semiconductors towards this IC. So we can able to consider this IC as the highest level, then that IC, the lowest level for this IC is a module. To reduce the complexity of the design, they will divide into different modules. Then modules are designed into the gate level. The gate is going to be designed into the circuit level. Then finally we have a device level. So when we are coming into device level, this device plays an important role towards the IC, and the semiconductor is also plays an important role in this device. So what is going to be the device here is it's going to be the field effect transistor, and we nowadays we are using different field effect transistors, different versions we are using. And this is a basic version is called as a MOSFET, maybe traditional version. So it is a metal oxide semiconductor field effect transistor. So we are talking more into the technology here. The technology, what meaning here is the distance between the two terminal here or channel length. Maybe if we are in 5 nanometer or 3 nanometer technology or 19 nanometer technology is nothing but the distance between this source and drain. That is nothing but the channel length what we are using. So according to this channel length, all other parameters also going to be scaled down so that we are able to get impact towards the IC level. So this is a fundamental block for all the IC where the semiconductor plays a role in our day-to-day life. And we all knows about this Moore's law that number of transistor and an integrated chip is going to be doubled for every 18 months. And it was predicted in 1960s. So we can able to increase the number of transistor by reducing its size. So why we are going for this reduction of transistor sizes, we are able to get like smaller device or compact device, and we are able to get more faster or very fast devices, and in the money wise also we are able to get the cheaper one. So these are the major advantages why we are going for this device scaling or device miniaturization. Apart from that, we have like a second level advantages also. So these are all the main advantages why people are going for this device scaling, and the industry also looking for it. And here I have like an high level overview for this scaling or the Moore's law application. So here we are able to see like in the older days how this ENIAC computers were there, and we know like we might be studied previously what is the functionality of this and what is the size of the system we used in the older days. And currently we are using like very compact laptops, and the functionality wise also which can be more, and it can be used for more functionality. So this enables our this can be achieved by using this device scaling. The number of transistor whatever we are using is, we are keep on reducing the size, and the number of transistor we are keep on increasing, so that we are able to achieve the more functionality with the smaller size. So it's a very good example for the system transformation from the initial days to the current days. And here I have a comparison of this 50th year of Intel's microprocessor. So 1971 is the first, the Intel's first microprocessor. They were developed first microprocessor. So Intel 4004, and 2021 they have 12th generation of i9 processor. So here I just have a comparison of number of transistor what they were used. A semiconductor device what they were used is 2300 transistor, and here they were used 7 billion transistor. And the die size is what they have as IC size. So this is 1.2 centimeter square, and this is 162.75 millimeter square. And the frequency is about how fast the device or the microprocessor can work. So this 0.7 megahertz, and this is for 5.2 gigahertz. So how we are able to achieve this higher speed with this smaller size? So you are able to see this is in centimeter square and this is a millimeter square. The importance here with the technology node what we are used. So in the previous days or older days, the first microprocessor whatever they were fabricated is with the technology node of 10 micrometer, and this is the this 12th generation i9 processor, they had a technology node of 10 nanometer technology. So with this variation they are able to use more number of transistors also. So when we are keep on increasing the number of transistor for every operation of our functionality, if you want to implement internally, the multiple number of transistor need to be switch on and off. So if we are keep on increasing the number of transistor, we are able to use for more functionality with the smaller space. So this is an example for the Intel microprocessor, and it shows like an importance of Moore's law and why we are going for the device miniaturization also. See, the device fabrication or transistor fabrication plays an important role in this. When we are going for different technology, the cost is also plays an important role for the technology or fabrication. So the cost fabrication for this 10 nanometer chip is almost like $170 million, and for 7 nanometer chip it is $300, and for 5 nanometer chip is $500. So we are able to see, like, with this cost variation, whatever it's happening for this different nanometer technology, the more second laws were defined, like the cost of the semiconductor fabrication plant was doubled for every 4 years. So this may be like 3 nanometer technology is around $700. So it's about the cost fabrication cost. It's going to be doubled for every 4 years. Is nothing but for different technology, it's going to be doubled. So with that, they are having like more second law in terms of the cost of fabrication of technology. So when we are speaking about this device miniaturization, so like an IEEE, we have a forum for this semiconductors also. It's called as ITRS. It's an international roadmap for the semiconductor. So this international roadmap of the semiconductor is also retired with the Moore's first law, and they have a new forum called as IRTS, is nothing but International Roadmap for the Devices and Systems. So this forum, it's like the future technology, what's it's need to be, and what is an industry perspective, all those things, it will be defined in very well advanced. So we are able to see like maybe always we are in around in this band 20 to 25. So in till 2034, it's almost defined like, and here we are able to see what is the technology they were in. We are in almost 3 nanometer technology, and in future it's going to be 2.1 and 1.5, 1 and 0.7 equivalent also. So these are all the future technology they were planning of that. Not only with the technology, what type of device or what type of architecture they are going to use also, it was listed. So it was the prediction it's given from the forum. So based on this, the research is going on, and the feasibility of fabrication, there might be small variation with that, not only with the device and the technology what we are using. So what should be like a different digital blocks or area of that, and the cell size, SOC area scaling, CPU frequency, that is nothing but how fast the device need to work, and other parameters, the important parameters needed for the fabrication of chip or the functionality of chip is also almost defined with this forum. So this is called as a fundamentals, or it's a reference for the future device. So these forums were created by the industry experts from different semiconductor foundries. So we are able to Google and we are able to get the information. It will be updated in a regular manner. As I discussed, like currently they were using FinFET technology. We might be all heard more about this FinFET technology. And in the future and currently they were doing the fabrication for this nano sheet also, or it is called as a gate all around architecture. So in future, it's going to be like a architecture named as 4-sheet, is nothing but, like all these VLSI devices are having CMOS technology. Both N MOSFET and P MOSFETs need to be combined together to perform its functionality. So this 4-sheet is having both NFET and PFET are integrated into the same structure, and the dielectric wall is placed here to separate this NFET and PFET. So both the device can be fabricated or integrated in the same structure, so that we are able to accommodate more number of IC with that, more number of transistor, so that it can be used for more functionality. And about the another architecture is nothing but complementary FET. This is completely different from the CMOS technology. CMOS technology is complementary metal oxide semiconductor field effect transistor. This is complementary FET, is nothing but both NMOS and PMOS device are stacked on top of each other. So here you will able to see that PFET, maybe pink color, and the top of this NFET were fabricated. So the gate is available between those two PFET and NFET. It's going to be common for both the device to work its functionality. So these two architecture is going to be the future architecture where available more into the research. And here I have like the current technology, what it was developed by the IBM. It's like 4.7 nanometer technology. It's for gate all around nanosheet technology. So it's like STEM view. So since it was in very smaller size, So this is a fabrication or fabricated device we are able to see, and here you are able to see like the stacked architecture similar like whatever we have here. So all these uh, individual here slides are sorry individual strips are having three nano sheets were combined together in the single gate. So like that we are able to accommodate more number of transistors to perform this more functionality. And here I have the uh, future roadmap, like what it will be in future apart from this nanotechnology. So here you are able to see like this N7, N5, N3. So it's representing the nanometer. So 7 nanometer, 5 nanometer, almost we are in 3 nanometer fabrication yet to come for commercial, and 2 nanometer is also were available for the future commercial purpose. And for the future they were planning for this A is nothing but Angstrom's technology. A14 is nothing but 10 to the power of minus 10. We all knows like nanotechnology is 10 to the power of minus 9 nanometer, whatever we were discussing. So 2 nanometer is 2 into 10 to the power of minus 9. So next is going to be Armstrong's technology is nothing but 10 to the power of minus 10 meter. So it's going to be like 0.14 nanometer technology. So the future is going to be like Armstrong's technology. And not only with the technology increment, we have continued dimensional scaling also. The metal pitch, how it's going to be between the two different metal layers, since interconnections also plays an important role when we are using more number of transistors. So that also it's need to be considered for this future technology. And the device and the metal initiation is also maybe in this I was discussed more into the previous slide how the nano sheet, it's the structure of nano sheet and fork sheet and the uh, complementary FET. So this architecture how it was there, maybe I was discussed in the previous slide. So when we are having more number of transistor into a single IC. Maybe now they are dealing with the billion of transistor into an IC. So when we are keep on moving for the smaller size, the number of transistor is also going to be increased. So the interconnects also need to be plays an important role, since all the transistors need to be connected with the other transistor to switch on and off, and the power supply is also need to be given for the transistor to switch on and off. So with that, the complexity of the interconnections also plays a important role. So it's need to be correctly placed, and the interconnections need to be given properly to have a minimum sizing of the IC as well as more number of transistor into that. Then here I have a high level overview for the industry, or what are the different foundries were working in the semiconductor fabrication. So here like TMSC is a Taiwan Semiconductor Manufacturing Corporation, Samsung, Intel, MSIC, then HLMC, Global Foundries, UMC. So these are all the different foundries were working into the semiconductor industries. And what is the current technology they were looking for it, and the future technologies also they were planning for 2 nanometer and future. It's almost all of these industries were working with the FinFET technology currently we were having. And this TMSC were almost having this 3 nanometer technology gate all around architecture. Is nothing but this IBM architecture, whatever I shown previously. So at the finally, I want to give some summary for the talk, whatever I have given. Like, so we have to see as maybe here we are talking more into this semiconductors. So almost the physics plays an important role here. So as a device physics, so internally it's going to be the movement of electrons and holes, how it is moving into that. So the electron movement, we all know that it's going to be moved from the valence band to conduction band. So with that, it's need to be analyzed and it's need to be studied how internally the device is working, or device physics is working. Towards that, more mathematical modeling is also important for the new architecture when it's going for it. And about this foundry and the research, there will be almost 3 decade difference. As I shown, like gate all around architecture, whatever currently the foundries are fabricating, The research papers were available almost 30 years back, and more research were going on, and almost because of this fabrication cost, whatever I shown, it's almost they were spending 4,000 crore amount for individual technology. So investing that much amount is not that easy when they are moving from one technology to another technology. So with that fabrication cost difference, there is a huge difference or huge variation with the research as well as the real-time production. There is lot of or more modelings. As I discussed, the analytical modeling or compact modeling is very, very important to learn the device physics, how internally the electrons are moving when we are exploring the new architecture. So there will be a lot of exposure is need to be done for the future technology, since not only with the field effect transistor, now research is going on with the different semiconductor also. So almost like graphene materials they were using, and high K materials also they were looking for it, and germanium materials, and group 3 and 4 materials, gallium arsenide, gallium nitrate, indium gallium arsenide. So such materials also they were looking for it. So when these material changes or architecture changes are coming into pictures, so more effort need to be given towards the learning of device physics. So that is also very, very important towards the research perspective. And very less research is going on in India towards these semiconductors, and maybe always like more very less group, and already this government were started the increasing the manpower towards the semiconductor. I think we all are know about this C2S scheme, whatever it is given by the government, chip to system design. So already government was started to increase the manpower towards this semiconductors. And for the student perspective, as I discussed, we cannot imagine our life without semiconductors. We are using more electronic devices. It's the semiconductor is going to be the fundamental for all our day-to-day life. So more scope is there for their higher studies. And finally, I want to conclude that, as I discussed, more device architectures were available in the research that need to be taken into the circuit level for the real-time application, as well as the fabrication is also lagging more in India. So maybe once the fabrication facilities were available towards the device level, it can be open for research to all of us. And I just want to give another input here, like in IASC and almost all the IITs, they have this INUP program, which is sponsored by the Department of Science and Technology. So that is a good scope or a good initiative were taken by the government to use the fabrication facility to all of us. So that can be explored a lot and utilized more to have a better thing. So at the end of this talk, I wish to extend my thanks to Alok sir, Seda and Ashwini ma'am from WIE to give this opportunity to share my research work in the high level. Maybe she told like constraint is only 10 to 15 minutes. I couldn't extend more towards that. Maybe in future, if it's possible, I can give more perspective towards this semiconductor, what current research is going on and what might be the future architectures and other thing. So thank you for this opportunity.
Many thanks, sir. Thanks. Sorry, Adila ma'am, it was nice talking to you. So we look forward to more of it. So I have some issues loading my slide deck. So I hope Prasuna madam is able to download as and how I speak. So without wasting much time, I will try to give you a very abstract view as to what my talk would be. In the absence of having anything to focus on, let me just start with, what my agenda for today is. So what I had with me, or what I wish to address, is IEEE history milestones, and IEEE history milestones from India. Why are they so few? A story that links to other potential IEEE history milestones, and the V Bangalore section initiatives for the year 2024. Seeing that we have already crossed the 8 o'clock mark, I'll try to be very brief. Meanwhile, Prasuna madam, I hope you have been able to download the slide deck. So I'll get started nonetheless with the IEEE milestones. It's a program that honors significant technical achievements in all areas associated with IEEE. The designated fields being engineering, computer sciences, and physical sciences, biological and medical sciences, etc., etc. There's a long list of things that are covered here. Yes, ma'am. Can you go to the full screen mode, please? And slide number 3. Yes, the agenda. Yes. So this is what I had, and I'll try to be very quick. So what we have is some milestones. Next slide, ma'am. Can you go to the full screen mode, please? Yes. So this is the vision of IEEE history and why we have that. So ma'am, can you go to the full screen mode, because there is animation. Shift F5. Yes. Thank you so much. So the first, next ma'am. Next slide, please. So the first here is the first millimeter wave communication experiments by Jagdish Chandra Bose that started in 1894 and went on for 2 more years. But in 1895, this was the best part. He demonstrated live, physically, in front of a big, auditorium at Presidency College, Calcutta, the transmission and reception of electromagnetic waves at 60 gigahertz over 23 meters through 2 intervening walls by remotely ringing a bell and detonating some gunpowder using a pistol. For his communication system, Dr. Bose developed entire millimeter wave components as spark transmitter, coherer, dielectric lens, polarizer, and a horn antenna with cylindrical diffraction gratings. So he chose quasi-optical millimeter wave frequency range with wavelengths of 2.5 to 5 millimeter, primarily because the radio waves he could study was within his laboratory of limited size, and it was available to him at Presidency College. So despite his shortcomings, the components and systems developed by him were far ahead of his time, and he made some outstanding discoveries about 130 years ago, most of which are now used for Earth and space links and remote sensing. Shown in the picture, next slide, is Dr. Bose's 60 gigahertz microwave apparatus and at the Bose Institute, Kolkata. And here left, next slide, please. Next slide. Yeah, this is the apparatus used, and this is the model that is there available at IEEE India office. The picture credits go to Harish Mysore and Sri Chandra of IEEE India office, along with Ms. Nagratna. So the next we have is 1899. Next slide, please. We have the Calcutta Electric Supply Corporation, which was established as the first commercial electric supply company in South Asia. This was in India in 1899, and the funny, I wouldn't say it's funny, this was not the first electric supply company. There was another one at Darjeeling. However, the CESC switched on to the 1000 kilowatt thermal power generation plant at Imambagh, Prinsip Street in the erstwhile Calcutta on 17th April 1899. So this was something that was, very impactful. And as much as we would like to talk about that, 10 years before this date was the first electrification or the electric light experiments that were carried out in Calcutta. Next slide, please. Next slide. Next slide. Next slide. Yeah, this is the picture of the company. Next slide. Here we see the plaque being opened for public view. It's a bronze plaque by the IEEE India IEEE history that was given. The 8.5 kg plaque was shipped from US. Here we see Director Ravi Chaudhary, IEEE India Chair Dr. Mathur Saab and Das sir. This was given in no, the previous slide, please. So this is momentous because this was actually given in 2021 amidst December 2021 amidst COVID. So this was actually the third IEEE milestone by the Kolkata section. The first one, next slide please, was for Raman effect. Okay, so yes, so on this very date in 1928, it was observed that when a beam of colored light entered a liquid, a fraction of the light scattered was of a different color, that is a different wavelength and dependent on the material property. So the applications of Raman effect are, very vast in current date, from non-destructive identification to early detection of life-threatening diseases. So again, thanks to Mr. Harish Mysore and Sri Chandrasekhar, we have, next slide please, a few photos here. Next slide. Yeah, this is the plaque that was given. This is visible at Subodh Malik Road, Kolkata, in the Indian Association for Cultivation of Science office. So the next slide is what we have there along with the this. So the next or the fourth IEEE history milestone, we only have 4 IEEE milestones. Next slide is the giant millimeter wave radio telescope, which was actually done and released to public use in 1994. The Tata Institute of Fundamental Research and the National Center for Radio Astrophysics, the NCRA and the TIFR, operates the GMRT, that is the Giant Meter Wave Radio Telescope, which has actually an array of 30 antennas, 45-meter diameter each, installed in an area of around 30 kilometers in Pune Taluk. And it's one of the largest and the most sensitive low frequency radio telescopes in the world. So in the current times, when people talk of a lot of communication, I feel this is something really very momentous, and it was done way back in 1994. This was dedicated to by IEEE Pune section to the GMRT on 30th March 2021. So the GMRT has been doing a lot of studies, and anyways, less said about that. Next slide. There are a lot of other potentials, 12 more milestones that are having a potential to become IEEE milestones. These are pictures again of the area. So you can see 30 arrays, and this is spread across 30 kilometer radius area, which is really tremendous. Next slide, please. So there is a lot of history that is grown at our own Karnataka state. One such story is starts in 1902. I'm really sorry, I'm talking a lot of stories, a lot about stories here today, but I feel at this juncture we should remember that then Asia's largest hydroelectric station was set up in Shivanasamudra. Sir K. Sheshadri Iyer Power Station, as it was known, was launched with a generation capacity of 700 kilowatts, which it far surpassed later to about 42 megawatts. This reigned as the largest. Next slide, please. Previous slide. Okay, so yes, please stay there. So this was not only the largest hydroelectric project in Asia for almost more than 50 years, but also it led to the creation of longest transmission line in the world in 1902 from Shivanasamudram to Kolar gold fields to light the mines there that were as long as 3,000 meters below sea level, covering 147 kilometers. So this itself is a record. Also, I would like to state at this juncture that Bangalore was the first city in Asia to have street lights lit by electricity. So the electricity that was generated in Shivanasamudram Samudram and later carried on to KGF was a lot. There was no storage capacity, so they actually brought it down to Bangalore and then electrified whole of Bangalore. And this was done using AC as opposed to the popular DC technology that was used then. So this is another reason that people actually discount why Bangalore had a rapid expansion. There was a lot less overhead that was spent here. So anyways, I just wanted to tell you that though we have a lot of technological advancements, it's never been identified. So maybe we have some things over here that kind of make sense. I wish to call upon you to just look at these faces and names and look at why, or why do you think that we as a nation fail to make a mark as impactful as other nations have. So next next slide, please. I just wish you could look at these faces. Yes, please. Next. So this is probably next. Click, please. Click. So this is Kati Karikó or Katalin Karikó, a Hungarian American who was awarded the Nobel Prize this year. So it is lesser known that for almost 20 years, she received no funding and faced a lot of flack for the work that she was doing. The work that she did was basically a lot of groundwork on in vitro transcribed messenger RNA mediations for protein replacement therapy that found a lot of use in developing COVID-19 vaccines. And she was actually senior vice president at BioNTech, which was the company along with Moderna that developed the vaccines. So she, along with Drew Weissman, received the Nobel Prize this year. But nobody accounts for the 20 years where she was not even given a tenure track. Next slide, we have Venki Ramakrishnan. Next slide, please. I don't wish to take more of your time, but this is a person that I would like you to actually look at and see his bio, because he started out as having born to very illustrious parents who were both scientists and world known. He went on to do his PhD in physics and totally shifted on to biology and started from the scratch with biochemistry and was awarded the Nobel Prize in 2009. People see the glory but not the grief and not the tears. So there was a lot of strife that this person actually underwent in order to work on his calling. So Narendra Singh Kapani is a name, next slide, that many might not know or might not associate with fiber optics, but his best known work, or he's the person who actually coined in the term fiber optics. Next, click please. So he is one of the 7 unsung heroes of 20th century for his Nobel Prize deserving invention, the fiber optics. So he used to be he used to work at the Indian Ordnance Factory and was awarded Padma Vibhushan posthumously in 2021. Another person that Dr. UC Niranjan has already spoken about is Dr. Rajeshwari Chatterjee. Yes, next slide, please. So this is her in her office at IISc, where she is not known as a Bengali, but a Shuddha Kannadati. She was the first woman to graduate as an engineer from Karnataka. During her tenure at IISc, she was a professor and later the chairperson of the ECE department. So it's a proud moment that we should actually look at these people and their work that they put in. And Sir Jagdish Chandra Bose, who actually, next slide, has an IEEE milestone to his name, was a polymath with interest in biology, physics, botany, and also writing science fiction. The Bose Institute has been a premier research founded by him with first interdisciplinary research center in Asia. Imagine a young boy who attended the University of London to study medicine, having to give it up due to health issues. So, however, he didn't give up his hopes and went on to Cambridge instead, collaborating with Nobel laureate Lord Rayleigh. On returning back, he joined Presidency College of University of Calcutta as a professor in physics. And despite racial discrimination, lack of funding, equipment, he carried on his scientific research and made a lot of progress in research into radio waves and microwave spectrum, and was the first to use semiconductor junctions to detect radio waves. It may be noted that his notable work on microwave was published almost 60 years after his death. So, having exhausted my names and faces for you to connect with, I only have this to share with you. Next slide. Next. Please skip. Yes. So collaboration is the only way. And it all starts with questions. And to ask questions, there is no silly question. You only need to have the courage to stand up and ask. You need to be bold. Next, please. And more fundamentally, there has to be work that needs to be done. So this is a clipping that I took from Rico Chan, a manga or a comic book from the WIE initiative that speaks about surrounding yourself with positive thought. So here we are from the Women in Engineering, EXICOM of the Bangalore section. Next slide, please. Next slide. So here we are, women and men from all works of the industry, academia, as well as studentship, coming together as a team, having done quite a bit from the past years, and here we are. So I leave the context for you to make a note, and I'm really sorry for having overrun the time, but wishing you all again a National Science Day, a very happy one at that. And the takeaway message from today that I would wish all of you would take is that consistent performance will certainly be awarded. Thank you so much. So I wish to place on record my thanks to Mr. Harish Mysore, Ms. Nagratna and Sri Chandra for the picture credits as well as sharing details. Thank you so much. So without much ado, may I call upon Ms. Supriya?
Hi, Ashwini. Good evening, all. On behalf of IEEE Women in Engineering Bangalore section and CEDA Bangalore section chapter, I extend heartfelt gratitude for making the National Science Day 2024 a significant success. Our special thanks to our chief guest, Dr. Srinivas T, and our insightful speakers. Dr. U.C. Niranjan, with his deep insights into the achievements in Indian science, set the stage for an informative evening. Dr. Vimla P. shared recent technological advancement in semiconductor space, providing valuable insights. Ashwini VR, Chair of IEEE Women in Engineering Bangalore section, shared perspective on IEEE milestones in India. A special thanks to Dr. Vijayalakshmi for her guidance and support to V initiatives. We also express our gratitude to the EXICOM members of IEEE Bangalore and IEEE Women in Engineering for their continuous support. I want to express our appreciation to Dr. Usha Rani for the warm welcome and the opening remark. This celebration highlighted the achievements of Indian scientists in indigenous technologies, and your presence made it truly remarkable. Let's continue collaborating for a technologically empowered society. Thank you all for being part of this special event. Thanks again.
If all of the presenters can, all of you can kindly switch on your video, it would be really great. Can we have a group photo, please? Yes. Madhu, Prasunna ma'am, are you able to take snapshots?
Yes, ma'am, I'm taking. Yes, just.
Thank you so much.
Yeah.
Thank you very much.
Thank you all.
Many thanks to all the speakers, Mr. Alokidas, Dr. Srinivas, and all the participants and attendees for your patient audience.
Madam, I request you to switch on your video.
My video is not available. I'm
Yes,
sorry.
no, madam, no, it's not available.
Oh, I'm really sorry. Okay.
Yes, ma'am. Thank you all. Thank you.
Thank you.
Yeah.
Thank you, one and all.
Many thanks for joining.
Thank you.
Can you stop recording? Host Prasunna madam, can you just stop recording before exiting? Yes, thank you.